I have found many videos on how to plot pressure and Mach contours using ParaView. However, I did not find much on how to create line plots such as convergence history, force history, and the pressure coefficients on an airfoil or wing. This video will demonstrate how to plot pressure coefficients and compare them to experimental values using the M6 wing as an example. Now, it's quite easy to plot pressure contours on a wing. And what you're seeing here basically is two attached shock fronts combining at the tip of this wing, which is the M6 wing, and all you have to do is select one block of this 4-block grid in this case, and then choose one facet, which turns out to be the surface of the wing, and then apply color contouring, and if you wish you can also apply contour lines. Now the plot that I'm going to demonstrate how to create is this one here, where you have the experimental values of the pressure coefficient being compared to the simulation results, and on the same plot are friction coefficients from the simulation, and I'll show you how to add a right-hand scale for those quantities. And by the time you've finished this video, you should be able to produce other kinds of plots, such as a convergence plot, which is shown here. What you're seeing here is the ratio of eddy viscosity divided by molecular viscosity, and that the maximum value of that reaches a constant value on a coarse subgrid of an imported grid, and then also reaches a constant value on the full grid. And in this case, the normalized residuals are smaller by a factor of 100,000 than the initial values, and that even holds true for the turbulent variables, which in this case are K and omega. You can see that the lift and the drag reach constant values on both of these grids. And another measure of convergence, which is more useful for laminar flow simulations, is the maximum value of friction velocity divided by the far field velocity. That also approaches a constant value. Now, the data, the grid, and the experimental points that are used in this video were obtained from the NPARC Alliance Validation Archive. So I'll show you some details of what this grid is like. It's imported initially in plot 3 format, and the grid being displayed here has a no-slip condition on the wing and a pass condition on the the interface between a couple of blocks, and it has a far field condition as shown here, and the initial conditions are imposed using a state which is one of many which can be defined. Now I'll zoom in to this wing, and you can see that both the bottom and the top of the wing have been modeled in this grid. And since it's an imported grid, you have to specify the boundary, the wing chord and what have you. So in this case I've used the aerodynamic mean chord, which is taken from the experimental model, and given this mean chord, I found a point along the half span of the wing where the chord where the local chord was equal to the mean chord, and doing that I then just took the leading edge and trailing edge points from that span location, and initially I chose a quarter chord point for the aerodynamic center, and then I varied this value using simulations until I obtained a value of pitching moment which was close to 0. Because this is a 0 camber wing, the pitching moment will be 0 when the proper aerodynamic center has been determined. Since this is a fairly small, since there's a fairly small far field distance, in fact it's about 12 chords in the x and y direction and about 7 half spans in the z direction. I'm also using a vortex correction at the far field, and this is for this 3D calculation, it's a horseshoe vortex correction. So I'll close that. Now, since this grid was initially in plot-free format, I had to apply boundary conditions in some of the block faces. And for example here, just to demonstrate, I can apply the slip boundary conditions on the wing surface, which I believe is correct. And there you have it. But since I don't want to do that, since this is a turbulent simulation, I'll just change that back to none. Okay. Now I've also applied, connected the various blocks to each other using a secondary interface dialog. And having done that, I then noticed that the root chord from the grid was not equal to the root chord from the experimental apparatus, so I applied a rescaling factor to make them equal to each other, and then I exported the grid in CGNS format and also exported subgrids. And the advantage of this is CGNS also stores the boundary conditions and the block connections. So let's close that. And then in this case here, I've imported the CGNS mesh, and I imported the finest mesh, but for early simulation experiments I use the coarser mesh. Okay, close that. Now this simulation was produced using the SST turbulence model of Minter, and it was I used an implicit solution method, in this case without preconditioning. Now I initially ran the simulation on a subgrid, which in this case had half a number of cells in each direction, and I ran it for 2,000 cycles at a CFL number of 1 initially, but this was increased to 20 after 100 cycles. And then this acts as the initial conditions for the simulation on the main grid, which is the one you see here. And so in that case I ran for, as I say, 2,000 cycles, and he also outputted restart files. Now a restart file can be used to extend the simulation, and it can also be used to output values at different time steps. For instance, I could have used an interval of 500 cycles and then redone those outputs. So in this case, at some point I'm going to be, instead of restarting a simulation, I'll be redoing the output, in this case at 4,000 cycles, in order to change the some of the output data. So I'll close that. And now I'll just show you one of the output dialogues, and this is because I'll be using this in my demonstration. In this case I'm putting CP and friction, and I'll be normalizing X by the chord to match the experimental data, and also be reversing the sign of CP to match the experimental data. In this case I'm specifying a span-wise location of 0.777 and so on meters, and that corresponds to a half-span location of 65% of the chord. And I could also output this in different variables that I could be outputting. In particular, I could output the primitive variables such as density and velocity and so on and so forth, plus add the friction velocity. And that's because in certain cases you might want to compute friction in a different way. So in this case, in the standard manner, the friction coefficient is computed by taking the local pressure on the wall, subtracting the pressure at the far field, and dividing by the dynamic pressure. The friction coefficient is the product of the density on the wall times the square of the friction velocity divided again by the dynamic pressure. And this here can be used to make friction negative if friction velocity is negative, because the code outputs a negative value of friction velocity in regions where there is free circulation, i.e. a region of flow separation. So I'll just minimize that, and that's all I have to show you here. Okay, now I'm going to start showing you how to create the plots. So on here. So the first thing I do is get rid of this material, some of the plots. Okay, so the first thing I do is I input the data that I need to plot. And this will be the values at the wall from the simulation. The pressure, in this case at 65% of chord. And later I'll be showing you the results for 90% of chord, how to plot that without too much extra effort. Okay, so I apply that, and then I apply a filter, and it's always best to start with the values from the simulation. I apply a filter, plot data filter, apply it, and then I disable everything except CP, and I choose that it be plotted with respect to X over chord, and then the plot from the simulation on a fairly coarse grid. Sorry, I also should mention that I had to use a wall function for this simulation because it was a fairly coarse grid. An adaptive wall function to give me good results. And then I do the same thing for the experimental points. Okay, so I add the filter, data, apply. I turn off again everything but CP. Okay, and I use X over chord. Alright, but then I highlight CP. And I turn off the line. And I turn on a symbol, a marker. In this case it's going to be a square. And I set the size of the marker to 15. Okay, and there we are. Now I do the second, in this case the upper wall again. Plot data filter, apply it. Turn off everything except CP. Highlight CP. No line. Use a circle. Scale of 15. And then I go up. And again I plot with respect to X over chord. And there you are. Now I want to add left and right axis. Now the left scale, X and right and bottom scales. But first, before doing that, I want to add another variable. That will be the friction. I'll highlight that, and I change the lines to dash lines. Okay, now, and so now I also have to change this to the bottom right. Okay, so then you have your scale on the right. So I then put in the left axis or scale name, that'll be minus CP. Then I put in the name at the bottom, which is X over chord. Alright, and then the right axis name. And that's C underscore F, friction. Okay, and that's it. Now I have to save this, and I save it as a state. Now a state is used by ParaView to basically store all the manipulations that I've produced. And I will give this a name, M6 underscore CP3 to match the names of the experimental data, but I won't save it in ParaView's state file format, because then I'd have to use a text editor to edit the data. Instead I'll save it in Python state format. So I'll just save that. Okay, and then I load at a new macro, and that will be the state I just saved. And then we can erase this old material. And then I'll run that macro. And there you have it. Now, this is at a span location of 65%. And I'm going to show you how to do a plot at 90% of span. So the first thing I do is I edit the macro. And I go down and I change CP3 to CP5. Oops. Yeah, okay. All right. CP5. And then I file and save this as. Okay, first I have to navigate to where I want it to be. And that'll be this folder. And it'll be M6 CP5. Save that. Close that. Add the macro. Okay, and we'll get rid of this material. Run the macro. The first thing you notice is that the experimental data has changed, but the value from the simulation is not, and that's easy to fix. We just open another script. And in this script, we change the span-wise location. In this case, instead of 65% of span, it's going to be 90% of span. Okay, and that's it for this. And remind you that I could have output primitive variables and the friction velocity, which I'll show you the result of doing that a bit later. What was that? And while I'm here, I could, if I wanted to, output the flow field values, different variables, and then different locations where the cell centers, or in this case, the node values, and I could output a number of quantities, but again, in this case, I'll simply disable that. It's not needed, because the initial simulation output the values I needed for the contour plots on the wing. Close that. Save the script. Run it in background. And that's it. So now I go back to the plotting. Again, get rid of clutter. And rerun the macro. And then you have the match between experimental results and the simulation. Now, unfortunately, there is no experimental data for the M6 test case, but I can show you results of a 2D simulation, turbulent flow around an airfoil. Now, just load the state for that simulation, and that's going to be, let's see, here we are. In this case, you have, again, experimental points being compared to the simulation. This would be the pressure coefficient. In this case, the experimental values were obtained again from the NPark website, but the also the flow conditions, but the grid was actually generated internally using an O-grid, and you also have the experimental values, a few of them available to compare to the simulation results. In this case here, I did not use the standard method of computing friction. Instead of the dynamic pressure at the far field, I used the dynamic pressure at along the edges of the boundary layers, and that's quite easy to compute. It's basically a function of the pressure on the wall multiplied by the square of the isentropic Mach number, and that's basically the method, the way they computed the friction in the experimental results. So I'll just minimize that. Okay, now I'll show you one more way of creating a macro where you want to be able to apply the macro to more than one output file of a similar type. So the first thing again is we remove the clutter. And the first thing we do is we navigate to the input file, which in this case will be for inviscid flow around a NACA 12 airfoil. Okay, input. This will be the wall values. In this case, it will be on a fairly coarse grid. Apply. Now, before I do anything else, I've got my input file. I have to start tracing what I'm going to do next. So I go to Tool, Start Trace. Okay. Then I apply, again, a plotting filter. Apply that. And then I disable everything except CP. In this case, the friction velocity will be 0 because this is an inviscid calculation. And also plot it with respect to x over chord. Okay, and there you have your initial plot. And you notice that it's upside down from the way you usually make these plots. And that's easy to fix using ParaView. Oh, the other thing I should mention that the friction, computing friction for the turbulent RA2822 simulation was easy to do using the calculator function of the ParaView, using simple formulas. And so in this case, I have to reverse the direction of the plot. In this case, the title will be CP because I haven't reversed the sign of CP in the output. Pressure coefficient, and use a custom range. You choose that, and then you'll see that it is initially from -1.2 to 1.4. All I have to do is put in from 1.4 to -1.2. Okay, and that's basically, oh yes, I should probably label the bottom axis as well. So x over chord, Right, now I stop the filtering, the tracing, and a file appears, and I simply save that file, save it as. I then navigate to the macros folder, and I'll just name this test because I already have macros which do this. And let's close this, load the macro. Let's test. Okay, so now if I just run this macro as is, it won't work. I first have to load the file that I want to plot. And again, I load the original file, apply, and then I run the macro, test, and there's the result you had before. Now I want to run it for a finer grid. In this case, this will be grid which has 4 times the number of cells in each in the 2 directions. Okay, and run the macro, and there you have it. On a finer grid, you have a much more sharply defined shock, and you also see evidence of a attached shock underneath the airfoil. So I hope that's been useful for you to watch this video. Using this video, you should be able to easily produce a convergence curve, history curve, or any other kind of line curve using ParaView.